So let's continue the discussion last time where we started to talk about random variables. And before defining the random variables, we will have to define a probability space on the real line. And this is because later on the random variables, when we define it, it will map the outcome to real numbers. So after this transformation, we will deal with probability on the real line. So we will have to consider how to define a proper probability space on the real line. Now, basically, what is the, in this case, the omega set, the outcomes are real numbers. These real numbers corresponds to the different types of statistics characterized by the random variables of interest. Now, on this real line, how do we properly define a sigma field, and how do we properly define a probability law? So this is the fundamental question. And last time we mentioned that for the sigma field F, it is defined by the Borel, so-called Borel field on the real line. Now the Borel field is generated by open intervals. Open interval means that it's an interval that excluding both endpoints. This is a typical open interval. And when we say this Borel sigma field is generated by open intervals, this generate means that, as we have done in homework 1, where we start with some elements of in the outcome space, and then we started to generate the complete sigma algebra by following the rules required by the sigma algebra. So basically, we need to consider all possible complements, countable unions and intersections of open intervals. Right. So this Borel field is defined to include all the sets that can be generated by open intervals in this way. Okay. Either taking complement, taking countable unions, or taking countable intersections of open intervals. And here are some examples, some remarks on this Borel field. This Borel field, we usually denote it as capital B. It contains all open sets. Because we can show that any open set on the real line can be written by a countable union of disjoint open intervals. So here there are 2 points to explain this sentence. So first of all, what is an open set, mathematically speaking? So recall that a set S is open if for any point it belongs to this set, you can draw a neighborhood around this point so that the entire neighborhood is included in this set. There exists epsilon. You can find the epsilon neighborhood. If I draw a figure, now consider this open set 0 and 1. Pick any point in this open interval. Right? This open interval does not include 0 and 1. They are excluded from this interval. So if you pick any point in this open interval, you can always find a small, sufficiently small neighborhood so that this entire neighborhood is included in this set. If this can be done for every single point in this set, then we call this set is open. You can always find the neighborhood included in this set. So this is a very nice structure. And the fact is that every open set in R can be written as countable unions of open intervals. There's a this is a theorem, but we will not show the proof here, so it's out of the scope of this course. But mathematicians have proved this for us. Okay. So this shows that this Borel field that we considered, which is generated by open intervals in this way, and this complements countable union intersections. They are basic operations when we define the sigma field. So this Borel field at least contains all the open sets on the real line. And also, we can show that it also contains all closed sets. Now, for example, what is a closed set? Well, this is a closed set on the real line. Right? Well, this closed interval includes the ending points. But to show that this closed set is contained in the Borel field, we need to show that this set can be written as either complements, countable union, or countable intersections of certain open intervals. Right? We need to generate this. We need to rewrite this closed set in the form of open intervals. And for example, this can be done in this way. It's a little bit tricky, but we can think about this. Now, closed set, if I draw the picture, corresponds to this closed interval. And to generate that, I can consider these intersections. This is a countable intersection of open intervals. Each open interval spans over -1/n to 1 + 1/n. So intuitively, right? So -1/n is to the left of 0. It's to the left of 0. And 1 + 1/n is to the right of 1. So we are so imagine, you can imagine that these open intervals, they are a little bit wider than this closed unit interval. And then we let n range from 1 to infinity. So as n becomes bigger and bigger, these open intervals are approaching the boundaries of these closed intervals, and we take their intersection. And we can show that this intersection actually equals to the closed interval 0 and 1. Well, and here's the argument. First of all, we can see that the entire closed interval is included in every single such open interval, because this is strictly to the left of 0, and the right ending point is strictly to the right of 1. So the entire interval is strictly included in every such open interval. Right? Because it is included there, so by taking the intersections, we can at least say that this closed interval is a subset of the entire intersection. And then the second step is to argue that if you pick any point beyond 0 or 1, for example, if you pick any negative point, or any point that is strictly bigger than 1, they will be excluded in this intersection, because you can always figure out a sufficiently large enough n such that that open interval will exclude that point. So this is a thought experiment. You can argue, you can prove this in a rigorous way. So the first step is to observe that this interval belongs to every such open interval. Therefore, by taking the intersection will include this closed interval. The second point is to consider any point that is either to the left of 0 or to the right of 1. Then we can always find a sufficiently large n such that this open interval such that these 2 points does not belong to this open interval. As n becomes extremely, that we fix any arbitrary epsilon, but I can let n to be extremely large, so that this number is smaller than 1 plus 1 over epsilon, while this number is bigger than negative 1 over epsilon. So in the end, any other point outside of this closed interval will be eventually excluded by such intersection of this open intervals, because this n goes to infinity. So you can always find open interval that excludes all the other points. So this shows that closed sets, intuitively shows that closed sets can be written in the form of open sets by taking intersections. So therefore, this Borel field that we considered actually contains all the open sets and closed sets, which is a very reasonable structure, very simple structure. So the final, to summarize, this Borel field contains the following forms of intervals. So all these intervals can be shown to be included in this Borel sigma field created for the real line. And you can see that, of course, there are open intervals because Borel field is defined, generated by open intervals. And there are half open, half closed intervals, half closed and half open intervals. So, which means that all these types of intervals can be written in terms of open intervals in a certain way by taking either complements, counter unions, or counter intersections. For example, here I can explain this for this one. This half open, half closed interval, we can generate it by the complement of this open interval. The complementary part is this is bigger. This means strictly bigger than A, right? So its complement is less than or equal to A. So it's a complement of this open interval. And for this one, half closed, half open, but this is finite. B is finite. This one can be following a similar construction. I can generate it by taking intersections of all these open intervals. Well, the right-hand side are the same because it is already open. Now the left-hand side here is closed. Therefore, following the same strategy as we did here. Whenever we have closed ending point, we can approach it by this sequence of open intervals from the left-hand side. So here we approach A from the left-hand side by this sequence of open intervals. And the other parts, these are symmetric. And this singleton, this set contains a single element. It's a single number. Well, this single number is not an open set because if you pick this is the only element in this set. Now, if you draw a small neighborhood around it, apparently that entire interval is not included in this set. So this is not open. This set itself is not open. But we can write it in this way. I'm considering everything except for A, which can be written as a union of these two open intervals. Everything strictly smaller than A and everything strictly bigger than A. Taking the union, this is every number excluding the number A. And then I take take complement. Therefore, therefore this set is generated by open intervals. This is open, this is open, and we are using union and complements, which is allowed in the Borel sigma field. This is union complements intersections, they are all allowed to generate these sets. Therefore, this set is also, by definition of the Borel field, it is also included in the field, which makes sense because at least we must be allowed to discuss the events that corresponds to a single real number. We have such cases. So therefore, this Borel field, which is generated by open intervals, actually contains a lot of different types of intervals. So it has very rich structures. And then we can define the probability space over the real line as follows. So for the outcome space, we consider the real line, and for the sigma algebra, we consider this Borel field. And this probability law is roughly the integration over intervals. Well, basically, you can understand it as kind of measuring the length of those intervals. We will see some examples later. So once we have this Borel field, we can find a proper probability law. For example, we can consider the bus arrival example. The bus arrives between 0 and t randomly. Uniformly and random. That's it. So every time between 0 and t is equally likely to be the bus arrival time. And apparently the omega space is this interval. This is the set of all the outcomes bus arrival time. And then the sigma algebra, we can take it as the Borel field. So restricting the Borel field that we discussed previously within this open interval. And take the Borel field over this open interval. And the probability law can be defined as for any event that is defined to be this open interval. This event means that the bus arrives between A and B. Right? For such an event, this is an event, and this event is a valid event in this Borel field, because the Borel field, as we discussed just now, this field contains at least all the open intervals, right? And this event indeed can be generated by open intervals. So this event is included in the Borel field. And then for this event, we can define the probability as, well, because it's uniformly at random. So it's basically considering the length divided by the entire time interval. The bus arrives at any time between 0 and 2 uniformly. So therefore, this event may occur with this probability is basically the length of this event divided by the entire time interval. So this is a probability space that we can define over the real line for this example. Because in this case, the outcome space is, as we said, the modern probability theory, one of the major novelties that we can handle these continuous cases. These intervals contains infinitely many number of outcomes. So we can handle this by introducing this Borel field. This is a very, very important concept in the modern probability theory. Okay, so then here we specify how to define this probability space over the real line. And then we can formally define the random variable. So random variable is actually defined in a very before we define it, I think in the introductory level probability process, we kind of call random variable as anything that is related to, that involves randomness. But here we need to rigorously formally define this based on the probability space that we constructed. So the random variable is this: we have an experiment. And this experiment has a outcome space, signal field, and probability law. Like this is a probability space for this experiment. And this outcome space can be very abstract. May not necessarily be real numbers. It could be, for example, the test result of a certain patient, right? It could be either a positive sign or negative sign. So this could be very abstract outcomes. And then in reality, in many cases, the outcomes are very complicated. It may involve, for example, if this experiment is about the testing result of 1 million people, then we will have 1 million different signs. Each sign indicates a positive or negative result for certain people. But what we care about in practice is some important statistics of these outcomes. Maybe we just need to know how many of them gets a positive test result. Right? So we define random variable, or we introduce random variable to map each outcome in this experiment to a real number. So this is a function, and this function maps each outcome in the experiment. And this outcome could be anything, could be very abstract. We map this outcome to a real number, and this real number corresponds to the statistics that we care about. This is what we can understand and we can process by using computers or other tools in practice. But this omega describes the experiments of interest. For example, we have, if each outcome corresponds to the test result of 1 million people, then this is very complex. There are a lot of this is like a very big raw data. Now we use this random variable to extract some important statistics of that outcome, like the number of the number of positive tests in this outcome, for example. Therefore, we simply define random variable as a function which assigns real values to each outcome of this random experiment. So this is a mathematical definition. Random variables are mapping from outcome to some real numbers, which represents some statistics. Therefore, with this mapping, the original probability space under the mapping of this random variable, we will generate another probability space. For example, for each outcome in the original probability space, we feed it to the random variable, and then the random variable will produce a real number, and that we collect those real numbers for all the outcomes. Those real numbers forms the outcome space for each random variable. So we call it omega x. So this is the image of omega under x. And similarly, for these events, after the mapping, they also corresponds to some numbers in the in this probability space. And then we also need to define corresponding probability law for this probability space. More specifically, this omega x is defined as follows. We will explore all the possible outcomes in the original of the original experiment, and then we collect the real numbers produced by this random variable. We collect all these real numbers as the outcome space for this random variable. Okay. So the original outcome space omega collects all the possible outcomes for the experiment. And then for every such outcome, we feed it to the random variable to generate some real numbers. We collect all these statistics, all these real numbers into a set. These are all the outcomes, possible all the outcomes. This is all the possible real number outcomes for this random variable. So this is omega x. So the definition is very similar to the original omega. We are collecting all the possible values that the random variable can create for this experiment, basically. And this fx is defined in a similar way. So we are looking at all the possible events in the sigma algebra of the original experiment. Take any events from that sigma algebra, and then we measure and then we collect the corresponding set of numbers produced by this random variable. Okay, so it's basically an image of f under x. I will feed every element in this f to the random variable. So this is an event. And this event, by definition, contains a subset of outcomes. Every outcome will, for every outcome, the random variable will extract a statistics, real number, right? we collect those real numbers to form a subset of real numbers. And this subset is a corresponding event under this new probability space, in this new probability space. And the sigma algebra generated by these events is the fx. And then lastly, to define the probability law for any such event as in this new sigma algebra, we define probability as so we basically trace back into the original probability space, find out which event, what is the event E in the probability in the original space that generates such event S. And then we assign the probability of that event in the original probability space to the probability of this event in the new space. So it's a one-one correspondence. From this S, we look back into the original space, find the corresponding event E, and then we assign the corresponding probability to this probability law. Okay. So basically, to summarize with one sentence, we are basically generating a new probability space under this random variable. Because it is a mapping from every single outcome to real numbers. So here, this omega x and fx, their elements are basically numbers. So let's consider a simple example to illustrate this such a transformation. We consider this experiment, which is a two fail coin flips. We flip a fail coin 2 times. So we know that for this experiment, the original, the outcome space for this experiment has 4 different outcomes. Okay, so this is the original probability space for this experiment. And each happens with probability 1 over 4 because it's a fail coin. And we assume the two trials are independent. Okay, so this is the probability law. Now let's consider a random variable x. Now, for example, I can define the random variable x as the number of heads I define a random variable as the number of heads that I observed after I flip these 2 coins. Right. So this is the statistics that we talked about. When you do such experiments, what you observe is observation of head and tails. Right. So it's a very abstract observation, and we may have 4 different such 4 different observations in the outcome space. And we only care about the number of heads that we observed in each experiment. Right, so based on this definition, this random variable will map this outcome to 2. Because this outcome has 2 heads. and this is 1. Well, this is 0. There's no head is observed. Right? So you can see this random variable, when you define it in this way, it implicitly actually corresponds to such a function. This function maps every outcome to a number. And this number is defined as the number of heads that we observe in the outcome. Right, so this is a mapping from omega. You go back here, this is a mapping from omega outcome to a real number, depending on how you define such a random variable. Therefore, you can see that all the possible outcomes for this random variable, this omega x, we only have 3 cases, 0, 1, 2. Right? Because this x means the number of heads that you can observe out of 2 trials. So you may have 0, 1, or 2 heads. Right? These are all the possible outcomes for this random variable. And because this is a finite set, the sigma algebra, we can just consider it as the power set of omega x. So this is very simple. And now, when we talk about, now let's look at the probability. The probability assigned, the probability law that we generated for this probability space is defined as follows. For example, if I want to look at the probability of this event, which means the probability that the number of heads that we observe is 0. And by definition, we need to go back to the probability space of the original experiment, try to find out the corresponding event there. So if you look at this random variable, x equals 0 means that we observe 0 heads in the outcome. So the only event, the only case that corresponds to this one is when the outcome is 2 tails. And this is an event in the original probability space. So I will measure the probability of this event using the probability law assigned to the original probability space, which is 1 over 4 for each outcome. And then this probability that is assigned to the original probability, original experiment, but it is further assigned to this probability of this random variable. So this is how we figure out the probability of random variable. We go back to the original probability space, find out the corresponding event, and then evaluate the probability of that event using the probability law of the original experiment. For example, we can also consider this event. This event means that I'm looking at the probability, well, the number of heads is bigger than or equal to 1. So this means, in this case, it is either 1 or 2. Right? Because x can only take these 3 numbers. So we can either observe 1 head or 2 heads. And these cases, and then I'm going back to the original probability space, trying to figure out what outcomes corresponds to these scenarios. So here it says either we have one head or two heads. So we look at outcomes in the original space. Here we have two heads, which is okay, one head and one head. So these three are the corresponding outcomes that can generate these cases for the random variable. So we collect all this. Right, so this event in the original probability space corresponds to this event in the probability space under the random variable. And then we calculate the probability in the original space. Right? Because everything is uniform, so it's 3/4. So whenever we deal with random variables, right, always go back to the original space, find out corresponding events, and then we measure the probability there. So another example, which I will not go over all the details, is very similar. So here we throw two fair dice. Two fair dice. So everything is pretty much the same as this coin flip example. The only thing different is that the outcome space is much bigger. So for this experiment, we have, well, each trial has 6 outcomes. We have 2 trials, so we have 36 outcomes. We have 36 outcomes. And it's the same thing. We can define random variables depending on what type of statistic we are interested in. For example, I can define the random variable x1 as the sum of the 2 outcomes. So you roll the dice twice, 2 times. Every time you get a number, right? You sum them up. That is the random variable I care about. For example, for this outcome, the random variable corresponds to 12. Right? It's the sum of the 2 observations. Right, so this is how we define the random variable. Now for this outcome, it is 1 plus 2 equals to 3. So this defines a mapping from each outcome to a number. And you can calculate, you can figure out the outcome space for this random variable, okay? Depending on how many, by summing up the integers between 1 to 6 with different combinations, right? How many different combinations can you have? And we can also define x2 as the product this is another random variable that cares about the product of these 2 outcomes. So in this case, for this outcome, this random variable will produce 36. Right? And this will produce 2 times 4, which is 8. Right? So this is just an example to show that the random variable in practice really depends on what type of statistics that you are interested in. And in the homework and all the remaining lectures, we will see this type of events very often. Okay. So we have this omega fp of an experiment. And we have random variable x defined, introduced for this experiment. Now we can look at this event, E. And we usually use this notation. Okay. Is the set, because the event is a subset of the outcomes, subset of this outcome space, right? So we need to collect some elements from this omega. Now this event is defined as follows: is the set of outcomes omega such that the statistics extracted by the random variable of this outcome is less than a given number x. Right. So this event is defined in terms of the random variable in this way. It's collecting all the outcomes such that the corresponding random variable will be less than or equal to a threshold. For example, we care about, in this example, right, we care about all the outcomes. Well, if we consider this random variable, sum of the two outcomes, we define the events as x1 is less than 10. This event means that collecting all possible outcomes, well, the sum of the two numbers will be less than 10. And by following that, you can figure out what are the which outcomes are included in this set. So we will see this event is a subset of the omega space, but it is defined through this random variable. And I want to briefly talk about what is a valid random variable. We define random variable as a mapping from omega to real numbers, but there are some rules in order to be a valid random variable. The first rule is that for any threshold x, this set, the set that we just talked about, must be, this event must be belongs to the signal algebra. But otherwise, this is not it is not a valid event, and we cannot discuss this type of events, which is very, and these events are very important in practice. We see them all the times. So we have to make sure that this random variable, this type of events created under this random variable must be a valid event in the sigma algebra, which is a reasonable requirement. The second requirement is that it's a boundary, kind of a boundary condition. Means that the probability that the random variable takes infinity values is 0. And this is a boundary condition. And when we write this notation, again, when we write this notation, it essentially means translating this back into the original probability space. We're trying to figure out in the original probability space, what is the outcome that generates such a random variable. So this is the event defined in the original probability space. This collecting the set of outcomes in the original space such that the corresponding random variable takes positive or negative infinity values. So these two probabilities, they actually mean this. This is well defined in the original. It's well specified in the original probability space. Okay. But this is a boundary condition intuitively. We don't need to care about these infinity cases. Now with this, we can start it to talk about distribution functions of random variables. The most fundamental one is actually the cumulative. This is related to the homeworks 4, I believe. Cumulative distribution function. Which we call CDF. This distribution function is associated with random variables. Okay. Let's give you the formal definition of this CDF. So CDF of a random variable, a valid random variable, X, is given by the following definition. This is a valid random variable X. We denote it as Fx, capital F, in the subscription we have capital X, and here we have small x. Right. Well, capital F means the CDF function. It's a notation for this function. Well, this capital F means the random variable. So this is the CDF function associated with this random variable. Small x, this is a real number, is the parameter of this random of this CDF function. Okay, so these three are different, have different meanings. But this is just notation. It is defined as the probability of this event. Okay, we usually write it in this way. Again, this is so let's explain this. This is the probability with subscript X, capital X. This means the probability law that we assign to the probability space, right? Under this random variable. And then in that probability space, we care about this event. This event is that the event that the random variable takes values less than or equal to X. But as we said, whenever we compute we need to compute probability in the capital X space, we need to go back to the original probability space. So this is more precisely defined as, I first translate this event from the random variable space to the original experiment space, which means I'm going to find out all the outcomes of the experiments such that the corresponding random variable is less than X. This collects a subset of outcomes in the original probability space. And this is an event in the original space. And then I evaluate the probability of this event using the probability law assigned to the original space. Right. Therefore, if you connect the left-hand side to the right-hand side, the CDF of a random variable evaluated at this small x really means the probability of this event. This is the event of all outcomes where the corresponding random variable takes values less than X. So you can say that this is a notation, and this is also a kind of informal. This is a definition under the probability space of the random variable, but this is the fundamental thing. So in the end, when we calculate CDF, we are really calculating this probability. Okay, always in the original space. So let's consider example. Where we roll a failed die and the omega space is clear. There are 6 different outcomes. Each happens with probability 1/6. And we consider this random variable. It's a very simple random variable. It is defined because in this case, every outcome is already a number, right? So the simplest random variable is identity mapping, which maps this number to the number itself. So this is a valid random variable, identity random variable. Therefore, in this case, we can see that the probability, for example, probability of the random variable takes value 1 equals to, we know that all the outcomes happen with equal probability. So this really means, for example, this one, it means x equals to 1. So you have to, based on this function, you have to go back to the original space, find out the omega. So x equals to 1 because this function is a mapping from omega to itself. So this actually corresponds to the event that omega equals to 1. If omega equals to 1, x1 will be equal to 1. So the value of the random variable will become 1. So this is the outcome corresponds to this event in the original experiment for bit space. And then we evaluate the probability of this outcome. And by this definition, the die is a failed die. So the probability of observing this outcome is 1/6. That's why we have 1/6 here. And then the CDF function, which is given by the probability by definition, is the probability that this random variable is less than or equal to x. It's given as follows. You can sketch it. So intuitively, we can see that if this small x is less than 1, then no such outcome exists. So at least you will observe 1, which is 1, 2, 3, 4 up to 6, right? If this small x is less than 1, this event basically is an empty event. So that is 0. Right, so basically we can intuitively see that if x is less than 1, then it is 0. When this small x achieves 1, then we have this probability that the random variable is less than or equal to 1. Well, less than or equal to 1 only corresponds to the case where we have 1, because we only have these discrete outcomes. Right? It only corresponds to the outcome that the die generates 1, and that is 1/6. So at this one point, we have 1/6. So this is an instant jump. And between 1 and 2, as long as this small x is strictly less than 2, we always have this single outcome. If x is less than 2, the only case we can have is x equals to 1, right? Because we only have discrete outcomes. Therefore, this CDF is a horizontal line up to 2. And once x achieves 2, if x is less than or equal to 2, then we have 2 outcomes. Could be 1 or 2. And these 2 outcomes, the probability of these 2 outcomes is basically the probability of omega equals to 1 or 2, because x omega equals to omega in this example. Right? And this is the outcome of the dice. The outcomes of the dice could be either 1 or 2. This probability is 2/6. So at this point, we jump to 2/6. And then we keep jumping. So it's a step function. And this is 3/6 when x achieves 3. and between 3 and 4 keeps constant. Until we reach the last point, x equals to 6. Things here. And after that is always a constant. So this is the sketch of the CDF for this random variable. You can see that this CDF function is not continuous. It is not necessarily continuous. But later on, we will show that it is always right continuous. So this point, this is always continuous. We call this right continuous. When you approach from the right-hand side, it is always continuous. The other example is a wheel, and we consider the angle that the wheel rotates. So assuming this angle is uniformly generated between 0 to 2 pi, so the outcome space for the angle is anything between 0 and 2 pi, and each outcome occurs with equal probability. And we consider this random variable. Because the outcomes are numbers, so we can consider this a simple random variable, simplest random variable. And to calculate the probability such that this random variable takes values between A and B, but we need to translate this event back to the omega space. Now, because this random variable is an identity mapping, so this event, when translating back to the omega space, is exactly the same event by replacing capital X with omega. So so this corresponds to the event of the original experiment. This means when you roll the wheel, the angle is between A and B. And then we can compute the probability of this event in the original space, because we are given that the angle is generated uniformly at random. So based on that, we know this is B minus A divided by the interval 2 pi. And then let's consider CDF. By definition, it is probability of the random variable that less than or equal to X. And here we already figure out the probability law of this random variable. Right? This is the law of this random variable. So we can follow in that we have the following cases. If this x, small x, is less than 0, then we don't have. If this is less than 0, then we are looking at the event, well, this angle is a negative angle. We don't have such cases. So this is an empty event. Now, when x is between 0 and 2 pi, then this event starts to be non-empty. Okay? This is a regular range for the angle that we consider. And then this is basically x over 2 pi. Because Here is capital X less than equal to X. Here is capital X less than equal to B. So it's B minus A. Well, in this case, A is 0. We don't have on the left-hand side, we don't have constraints, but by default, this angle must be positive. So it's X minus 0 divided by 2 pi. If X is bigger than 2 pi, then basically we are looking at, then this constraint is covers every single outcome. If X is bigger than 2 pi, then it is guaranteed that the rotated angle is less than X. So this happens with this event. So this event will cover all the possible outcomes. And we know that for this omega event, it has probability 1 by the probability law. And we can sketch this CDF function. It looks like this. It is a continuous function. It's a continuous piecewise linear function. Right. So again, these examples, we are considering very simple random variables, right? But in other cases, right, when you look at this kind of probabilities, always, okay, when you look at this kind of probabilities, which is defined under the random variable, always translate it to the event in the original probability space. And then you evaluate the probability in that space. Okay. So this is like, given the range of this random variable, you need to figure out the range of the domain for that random variable. So sometimes we call this the inverse mapping. This notation means we are looking at the inverse mapping of X on this interval. This denotes the set of omega such that they can produce values between A and B under this random variable. So this inverse. This corresponds to this set. This is another notation to denote this. Okay. But again, because here we are looking at very simple random variables, so the translation is relatively transformation is relatively simple. Okay, so I think I will stop here, and I can finish the rest of the lecture 8 in the next lecture, and I will record a video for that. So in the afternoon, I will hold the office hour from 3 to 5 p.m. So you can log into the Zoom, and we can discuss more problems. And by the way, next Tuesday we need to discuss how to schedule the midterm 1, because midterm 1 will be should be done after lecture 9. So we will figure out a time for that. It's a take-home exam, 24 hours. So we just need to find a day that is available for everybody.